Now we're going to look at electricity as part of our principles module. The key objectives for this part of the session, I want you all to be able to match the symbols of voltage, current, power and resistance to the name, give a basic description of what is actually meant by voltage, current, power and resistance, and what they do in a circuit, and calculate the missing unit using the power law and Ohm's law triangles. So I'll quickly chat through first what is electricity. And electricity is essentially the flow of free electrons. And metals, particularly copper, are very good conductors because they have many free electrons, and copper is an excellent conductor of both heat and electricity. A flow can be created in lots of different ways, and we're going to briefly look at some of the ways that they can be generated now. Alternating current is normally created by rotating a conductor in a magnetic field, like you can see on the right here. So all of our power stations, coal, nuclear, wind and hydroelectric power stations, all use this method. They'll use movement to spin a conductor in a magnetic field, which causes the electrons to move backwards and forwards very, very quickly. And that creates an electrical current. The only exception to this would be our photovoltaic plants, which would generate something called the direct current, which we're going to look at now. So direct current can be generated in sort of two main ways, really. One is through electrolytic corrosion, and we're going to look at this in a lot more detail later on in the module. And that's essentially a form of corrosion where one metal, a more cathodic metal, breaks down a more anodic metal in the presence of an electrolyte, and the electrons will flow from the negative side towards the positive side, so from the anode towards the cathode. And that would create a direct current because all the electrons are flowing one direction, whereas with an alternating current, the electrons change direction very rapidly. Another way that our direct current can be generated is through light hitting a photovoltaic cell, and that causes the electrons to flow from the more negative side towards the more positive side. So electrolytic corrosion, like I've said, is caused by dissimilar metals. For example, a copper, which is generally more of a cathodic metal, and zinc, which is generally more of an anodic metal, being placed together in the presence of water, for example, which is an electrolyte. And an electrolyte is a material, a sort of liquid, that allows electrons to flow through it, electricity to flow through it, and water does allow that to happen. So how fast that corrosion occurs depends on lots of different things, but the main thing that has the effect is the position of the metals in the electromotive series. So we're going to look at this very briefly. Interestingly, any of these metals on here could potentially be an anode, and any of them could potentially be a cathode. It all depends on what two metals are together. For example, copper is generally a very cathodic metal, and if you put the copper with lead, for example, the copper would take the electrons from the lead very, very slowly over a long period of time. But if you put copper with magnesium, for example, there's a much bigger distance between these two in the table, so the copper would take the magnesium's electrons much more quickly than it would from the lead. Copper would also be the cathode if it was put together with aluminium. The aluminium would be the anode in this instance, and it would take the electrons quite quickly. But if you put aluminium and magnesium together, because aluminium is above magnesium in the electromotive series, the aluminium would then be the cathode, and it would then take the electrons from the from the more anodic magnesium, and that would happen over a fairly long period of time because these two are very close together in the table. Okay, so in electrolytic corrosion, the more cathodic metal breaks down the more anodic metal by taking its electrons. It can only happen in the presence of an electrolyte, which is a fluid that conducts electricity, such as water. And they use this process in batteries. Though generally speaking, in batteries, the electrolyte would be acids normally, because an acid would increase the speed of the electrolytic effect. How acidic or alkaline the water or the material that the anode and cathode are in would increase the speed of the electrolytic action. As with the temperature, if it's hotter, generally the electrolytic action is quicker. So yeah, it can be useful, electrolytic action, for example, in batteries, but it can also cause issues in plumbing systems. So if you, for example, you put galvanized steel pipe, which is covered, galvanized steel pipe is a steel pipe which has got a zinc coating on it to protect it from the water. And if you put that next to copper, that zinc coating would be electrolytically corroded fairly quickly, because there's quite a big distance between those two in the electromotive series. And then that would leave the steel exposed to the water, which could then sort of cause atmospheric corrosion. And if you can even have zinc being leached out of fittings. For example, brass is a mixture of copper and zinc. It's an alloy, but what can happen is the zinc can be sort of leached out of the brass fittings in a process called dezincification, which you can sort of see on the right here. So we've kind of looked at how direct current and alternating current can be produced, and we're going to now talk briefly about the different types of units used in the sort of calculations we might need to know around electricity. So the units are current, voltage, resistance, and power. We'll sort of touch on coulombs. We'll mention coulombs and energy, because they are part of, they make up some of the units we're talking about up here. For example, sort of current is measured in amps or amperes, but what current is, it's actually a flow of coulombs. It's a certain number of coulombs passing a point per second, and it's kind of similar with our power as well. Power is measured in watts, but it's actually the flow of energy. So it's the number of joules passing a point per second, and joules is the measurement of energy. Okay. So current is the flow of electrons. The more electrons flowing, the higher the current. And essentially the number of electrons is measured in coulombs. I can't remember the exact number, but basically 1 coulomb is like millions and millions of electrons. So if you talk about 1 coulomb per second passing a point, you're talking about millions of electrons passing that point per second. Current's measured in amperes, often written as amps for short, or even shortened to A. But in sort of our SI sort of units of measurement, or in their scientific calculations, we would use the symbol I, because originally current was called electrical intensity, and that's where the symbol I came from, and it's kind of stayed as the symbol I for current. Because current is measuring flow, 1 amp is the equivalent of 1 coulomb per second passing a point. So, here we go. A coulomb is 6.2 million electrons. So it's a rather large number of electrons. Voltage is what pushes the current around the circuit. It can be thought of as water pressure in a plumbing system, for example. So if you increase the voltage, the current will rise. If you increase the pressure, then more water will flow. There's a sort of parallel there between our electrical circuits and our plumbing circuits. Voltage is measured in volts with the scientific symbol of V. Resistance is essentially what's going to sort of slow down the current if you increase the resistance, you'll reduce the current. You'll also reduce the voltage. Resistance is measured in ohms, and it has the symbol for omega here as its symbol. And the scientific symbol they use in the calculations is R. Power is measured in watts, and watts is essentially the flow of energy through the circuit. Excuse me. Energy is measured in joules, and 1 watt is the flow of 1 joule per second passing a point. Got a very briefly chat through Ohm's law. So there's 3 major components required to make up an electrical circuit: their voltage, current, and resistance. If you know any 2 quantities, we can calculate the third using something called Ohm's law. And there's a nice video showing how to do Ohm's law on this slide here. Power law is another one we need to be aware of, and if we know any 2 of either power, voltage, and current, we can then work out the third one using the same principle as the Ohm's law. There's triangles to do this, and there's a very, very good video showing you how to do this on the next slide. Okay, so now it is time for your task. Make sure you watch those 2 videos first, okay?